in their work. They come from Duke University.
Is this working?
Yeah, it will not. You cannot really hear it, but
It's for the on. How do I? Don't want it to be too close, right? It's just back and forth, right?
There is a point there.
Should we be in front or we should move because you can't see? All right, so thanks everyone for, first of all, thanks to the organizers for giving us the opportunity to talk about the work we've been doing at Duke. So we're going to talk about the systematic or uncertainty that is, how would I say it properly, is killing us a bit in photometric redshifts. And this idea is buoyance. So what I would like to start by first defining what the sample variance is, because maybe not everyone is on the same page. So sample variance, you can think about it as an uncertainty that arises due to the fact that we observe only a patch of the sky. And maybe in order to understand it better, I try to draw it somehow, so bear with, like I hope I managed to do it. So let's say that this minty green background is the full sky, and then we have a survey patch or footprint that looks like this pentagon. And then you have your deep fields that are these three darker blue circles. So you see that the footprint is not, of course, covering the whole sky. So that's the first problem. The second problem is if we think about the modes, which are represented here in the, oh, there's a laser, awesome. Let's say you have this mode, so you can see that your deep fields are not capturing the full information from the mode because the mode is too big. And you can also think about the problem if your patch, which is, this is like overblown, right? In reality, it doesn't look like this. But if your patch is lying on a part of the universe where there is a void or some overdense region, so it's not really representative of your sample. So why does this matter? Again, I don't know if you've seen this plot, I mean, like 15 times, but it's a legendary plot by now by Boyan, and it's a very good plot. But just to emphasize, because you already know about it, this is the contribution of the sample variance. So basically, we need to try to make it smaller. And you might ask yourself, why? Well, different people care about this thing and for different reasons. I personally care about it because this is going to really propagate into the data vector and later into the constraints and cosmological parameters, because here you have the variance of the mean redshift, right? So the center of your bin is going to move around or be uncertain. If you want to see how much for example, the impact of the mean of the redshift impacts the constraints of cosmological parameters. Again, the paper that was just mentioned by Bitpadep, it's the paper led by TQ and some other wonderful people like Rachel. You can see exactly all of the impacts of the uncertainties of redshift, well, in photometric redshifts on the 3x2 point in terms of LSST. You really get the numbers there. So this is the motivation why we need to work on this. Now, oh, this is the wrong, right. So how do we deal with sample variance? So sample variance is not like some new thing that we just discovered, right? It's a problem. People have been, thinking about it and mitigating it. So the way DES is dealing with the sample variance is by, of course, as every physicist, you assume some, not spherical cow in this sense, but you need to assume a circle or field, whereas in reality, the deep fields are absolutely not circle. There are those are these tiny patches here that have very irregular shapes. They do not assume any bin, redshift bin correlations, and they do something that's called inverse variance weighting of multiple fields, and Boyan's going to touch up on that. So this technically works, but not perfectly, because it is a lot of approximations that goes into this, and this is also done in Fourier space. So in order to handle this, or to tackle, but Boyan had a very good idea, and I'm going to hand this laser thing to you. I think I have this. You have this. Awesome. So I'm going to just shut up. Just take over, Boyan.
So Our idea is to improve and extend this DES framework to account for realistic geometries. That is, for DES, we have 4 different deep fields scattered across the sky, and we include the spatial correlations between the fields. In the glimpse, I'm showing our method in this map. On the left, it is the original map generated from CAMB for the full sky. For each pixel, I'm showing the number density of galaxies in it. We perform a real space top hat smoothing filter in the real space of DES deep fields for each pixel. In this way, all the small angular scale like modes that is inside the deep field will be smoothed out, and only the large angular modes that is uncaptured in our deep field is left in the smooth map. We sum up all these uncaptured large scale modes, and that is essentially our sample variance. In the future, we also want to add cross redshift slice redshift correlations, and we hope our new method will provide guidance for survey design. So the first thing after we develop a method is to validate it. So here is the method validation. We're comparing our theoretical predictions, shown as the light blue line, to the measured variance using the mice simulation catalog, which is shown as the dark blue dots here. We show that they have good agreements with each other. We also inspect how geometry and separation affect variance. So in this 4 plots, we're actually showing the deep field of the same square degree in total, that is 20 degrees squared. But the geometry is different. For the first one is an elongated rectangle with 1 degree times 20 degree. The second one is 2 times 10 degree. The third one is 4 times 5 degree, while the last one, although 20 degrees squared in total, is actually a circular area. So we figure out that geometry actually has an effect in sample variance. So we find that 1 times 2, 20 degree, that is the most elongated rectangle, that is having the least sample variance. And this is because it is capturing like the most large scale modes like inside that elongated rectangle. We also are very excited to show our preliminary results performed on the real DES year 6 deep field. We compare this like on the same field, the current DES year 6 method and our method. The DES year 6 method is shown in the circular dots in the plot on the right, which indicates DES year 6 method can only deal with circular geometry. Our method shown as the square dots, showing that our method is good in arbitrary geometry. In the right plot, we can see that our method is slightly higher in sample variance than the DES year 6 method, but more robust. This is because the DES year 6 method assumes circular geometries, while the real DSD fields are actually bounded by RA and DEC. And also DES year 6 method combined the 4 different D fields using inverse variance weighting, and this may not be the best assumption to make, because inverse variance weighting is the best when the 4 different D fields actually captures completely independent information, which may not be the best case here, because the same small angular modes are actually captured by the different D fields, and it is the correlations between these 4 different D fields that is adding more information. We also tested our method with the DES year 6 method on circular geometry, which both methods performed well. We are seeing remarkably consistent results with each other, which is not shown here. And also, looking at the plot on the right, we can actually see as redshift increases, the sample variance decreases. And this totally makes sense because it is like the D fields are like a light cone. So if you're moving further in redshifts, you're actually probing more universe and decrease the sample variance. So before I go to the summary, I really want to thank the DES team and also especially to Marco Raveri for providing us the DES method code. And we are super grateful for that. So we want to reiterate again that sample variance is critical for the next generation surveys like Roman and LSST. We're extending and validating a general framework of DES Year 6, and our early results are super promising, and the full implementation is underway, in which we'll improve the galaxy matter bias modeling in the current method when generating the sky map. We're also want to include per redshift bin estimates and also cross redshift estimates for sample variance. And we are already doing very well with irregular footprints. We hope to apply our method in the survey design choices for stage 4 surveys. We will also willing to test how different supernova fields combination will lead to the least sample variance, and also test it on Roman-like configurations. We'll also propagate our sample variance to redshift realizations, and we'll use PCA or mode sampling in cosmological analysis to see how sample variance is influencing cosmological results. And thank you so much for your attention, and we really look forward to questions and feedback.
Thanks again. So just a quick comment. And the online people are saying that they cannot hear the question. So if you could please repeat the question one.
Yes.
So TQ, please.
Yeah, I have. So for your mice experiment,
Yes.
Is the field randomly selected in your simulation?
Yes. So for
Yeah. So let me finish my question. So is it randomly selected? I assume yes. And my question is, have people think about what happened if you select only field with overdensity? Because that's kind of how people decide where to do the deep drilling field is, more likely than not, there's a giant cluster that magnifies the background. So there's usually more galaxy in the deep field, in the training set. Have people look at whether that creates, more variance, less variance, or bias to the photo Z?
So I think to repeat TQ's question, so the first question is that how do I decide the mice data validations? Is that randomly selected, or is how are they selected? And the second question I think is that you are saying the deep fields have more galaxies because of.
Have you checked what happened if you choose your deep field at the overdensity?
Oh, so
it's only part of the mode, right?
Yeah.
If you only pick the overdensities rather than randomly.
Oh, so and the other question from TQ is what if I pick up the deep field that has overdensity other than mean density? So their uncertainty should be different, because if it's overdensity, the sample variance should be larger than if you are picking up a random area. Right. Yes. So first, the question is how the mice simulation. So we just cut the same areas of the mice catalog, and we estimate the number density perturbations per redshift slices for the cutted deep fields areas in that mice simulation. And we think that this is a very good way to validate our method. And the second question is how we are dealing with our deep field slice in overdensities, or it's a random picked place, because the overdensities or inner densities should have larger sample variance than the randomly choices. And I think this is I think this can be addressed by the galaxy matter bias modeling, because from the to the CAMB, because whether it's in overdensity or in inner density, the galaxy matter bias modeled from the real data set will actually be different. So if it's in overdensity, actually there will be I think actually more galaxy matter bias, and that will lead to a larger CLs, and that will make our results larger. So that would be very good if it's the sum up CLs will be larger than if it's randomly picked up. Just
we could what she suggested, we could try to not randomly select, but select, you know, a denser patch and see what comes out.
Yes,
And
definitely.
Then, yeah, that's a very good actually.
Yes.
Suggestion.
Yes. And
We have one more question about our next speakers. All right. Yeah.
Your legendary plot. Why does the highest redshift bin have the highest sample, like largest sample variance?
So the question is,
yes.
in the Boyan's legendary plot, why does the redshift bin 4 have the largest contribution of the sample variance?
yeah, I think that's a very good point. So you would like think, okay, so like if it goes like to higher redshift, as we previously showed, it's like having like less sample variance because you're probing more universe. But why like here it has larger? And this is because in the redshift bin 4, there's actually large color redshift degeneracies. So it's like this, like it's like kind of like spanning a large region, like from like redshift, like from like there's like degeneracies like that. It spans a long like redshift range. And also like if the tails like changes, it actually gives a large change in the mean redshift. So it's kind of like, this is because like it's like the redshift bin sizes, like, yes.
Does it imply if you change the combination of filters, can you break the degeneracy?
Degeneracy, yes, indeed. Like if it's like from DES year 3 to year 6, so year 3 uses only RIZ band because, but in year 6 people improve and add G band because PSF like improvements, and actually the degeneracy changes a lot and the bin overlap like decrease a lot because of the addition of G band.
All right.
I forgot to repeat the question.
Thank you. Sorry. Thank you so much.
Thank you.
Let's thank our speakers again. So our next speaker is Federica Carcitano from.
Okay. Good morning, everyone, and thank you very much, the organizers, for the opportunity of giving this talk. I am Federica Tarsitano, and I am a postdoc at ETH Zurich. Today, I will walk you through a few interconnected projects I have been leading in the context of the Euclid collaboration and in the framework of a new HSC medium band survey with the Subaru telescope. And I will highlight their potential synergies with Roman. In doing so, I will use a few science questions that will drive our discussion. In this first question, a key word is galaxies, as they are one of the main characters in the cosmic narrative of structure formation. And they are unique tracers of the large-scale matter distribution in the universe. In the next few years, Euclid will be able to provide shapes for billions of galaxies and build up synergies with Roman, with Euclid going wider and Roman achieving a greater depth. Indeed, the combination of both surveys will enable us to work with an unprecedented optical to infrared dataset in order to answer the main questions about the dark universe and galaxy evolution. In doing so, we need very well to manage key ingredients in our analysis that are photometric redshift and PSF model. They are crucial in order to understand the demography of galaxies, their properties, and to test cosmological models. Speaking about photometric redshift, the Euclid dedicated pipeline can be seen as a function whose domain includes external and Euclid data, and the output is photometric redshift estimates and N of Z. And in terms of external data, we can definitely mention unions, that is a collaboration of collaborations, including the Subaru telescope and the Dark Energy Survey. They are extremely important in order to calibrate the photometric redshift. Another product of the pipeline that relies on external dataset are galaxy spectral energy distributions. They are of great relevance in surveys such as Euclid and Rubin due to the chromaticity of the PSF, which means that any bias we introduce in the reconstruction can be directly transferred into the PSF model and ultimately in the weak lensing analysis. In this work, I focused on galaxy SED reconstruction using both template fitting and machine learning-based methodologies and assessed the accuracy against the requirement imposed on the PSF model. Here I show the results in terms of the bias on the SED reconstruction in redshift bins. One of the main causes of bias is the poor coverage of the VIS filter. For this reason, I explored the possibility of gaining in accuracy while using a new medium band filters, 16 in total, with the Subaru telescope. And as we can see in this plot, we can gain very much in terms of accuracy in galaxy SED reconstruction, and we can hit the requirement imposed on the PSF model in most redshift bins. This new HSE medium band survey consists in an imaging set of 16 filters covering the VIS window between 400 and 1000 nanometers. For observational logistics, these 16 filters are organized in 4 quadrants, 4 filters per quadrant. And the first one, including the bluest 4 filters, has been delivered in July and passed already all the tests in Hawaii. So it is ready for observational proposals. The next 2 quadrants will be ready by the end of the year, and we are currently seeking fundings for the last reddest filters. We plan 2 Subaru intensive programs. The second one will hopefully use the full set of filters. The first one, the bluest filters, for a total of 600 square degrees and 40 nights. We also coordinate with the Keck and Gemini community. With an HSE medium band survey, we can explore a variety of science cases, starting from cosmology, building a Lyman alpha emitter survey, and planning spectroscopic follow-up with the DESI and PFS. With the full set of filters, we might be able to provide a calibration dataset to improve the shape calibration and the photometric redshift estimates for surveys like Euclid, Rubin, and Rubin. Going beyond the cosmology, we can also target galactic archaeology and the galaxy evolution domain. For example, already with the 4 bluest filters, we will be able to study the galaxy population at cosmic noon when we register a peak in galaxy mergers and AGN activity. In order to foster the cross-institutional discussion about this new set of medium band filters, we have been organizing a series of workshops in collaboration with Hironao Miyatake and Atsushi Nishizawa in Nagoya University. The next workshop will be held in Nagoya in the first week of August, and the deadline for registration is just today. So you are very welcome to scan this QR code and join the discussion either in person or online. So far, I described an example of how these medium band filters can be very much useful in the context of photometric redshift for weak lensing analysis. However, more accurate photometric redshift can be key also in the domain of galaxy evolution, and in particular in dual AGN science. So in this second part of my presentation, I would like to walk you through an example. We can consider AGN as polyglot citizens of the universe, as their emitted radiation can be detected across the full electromagnetic spectrum. And a survey like Euclid is very fluent in a couple of these languages, operating in the optical to near infrared. And teaming up with Rubin, we can definitely target way better the accretion and feedback mechanism up to redshift 7, and we can definitely advance our knowledge in terms of obscured AGN and high redshift quasars. Among the most debated mechanisms that might trigger AGN activity, we find galaxy mergers. And interestingly, we think that they can trigger the formation of dual AGN system consisting in AGN at a projected distance of less than 100 kiloparsecs. Dual AGN are considered the progenitors of binary supermassive black holes that eventually coalesce, emitting gravitational waves. So far, we have been working with the dual AGN cases coming from serendipitous discoveries due to instrumental limitations. However, a survey like Euclid and furthermore teaming up with Roman, we will be able to build up a first census, a first systematic census of dual AGN systems and studying their properties and their evolutionary path as a function of cosmic time. In the context of Euclid, I'm actively working in the search of dual AGN system, just starting from the catalog of candidate red quasars that I developed in the context of the Euclid first quick data release in March 2025. In particular, I ran a peak detection algorithm on the Euclid images of the red quasars in order to find candidate nearby sources when one of them is a quasar and the other one is a candidate AGN. And then I proceed with a pairing phase, which means that we need to assess the proximity criterion. And in order to calculate the projected distance, we need photometric redshift. In particular, we work with the PDZ. Now, a naive approach would be based simply on the overlap of the PDZ. However, as you can see in these examples, in most cases, they can actually overlap due to the fact that they are very broad. So if we simply use this naive approach, we can definitely introduce a huge inaccuracy in our proximity criterion. And this is an excellent example of how more accurate photometric redshift could enable also an advance in our search for dual AGN system, and in particular, we would be able to build up a sample of dual AGN with a higher purity. In this case, in order to overcome these challenges, we are working with a combined metric that takes into account both the statistical similarity of the PDZ and their width-weighted overlap. In this way, we can match both statistically and physically the dual AGN systems without assuming any form of Gaussianity or symmetry. So already at this stage, we find very promising results. First of all, we observe that the 4% of candidate red quasars are actually in a dual AGN system, and their population peak around the cosmic noon. Furthermore, we observe that the mass ratio between the two objects in the dual AGN systems tend to unity when we decrease their projected distance. And our findings are very much in line with the comprehensive set of hydrodynamical simulations that is already available and tries to give predictions about the formation and the evolution of dual AGN systems. So to summarize, in this talk, I put emphasis on the fact that in the next few years, in order to unlock the full potential of surveys like Euclid and Roman, we need more accurate photometric redshift and galaxy SED reconstructions. And this can actually allow us to make an improvement in precision cosmology, as well as opening new windows in galaxy evolution and AGN science. And a survey like this new HSC medium band survey will play a key role in building up this bridge. So I would like to thank the organizer for this fantastic workshop so far, and I thank you all for your attention.
Thanks for this. You showed a plot where you had some metric of improvement from the medium band data on some SED metric. Well, can you say more about what that SED metric was?
Yes, so this SED metric basically is actually, it can be seen as an effective wavelength integrated across the full Vis filter. And the bias is basically created as the relative difference between the metric that is calculated on the simulated CD and the reconstructed CD.
All right. So let's thank Federico. And we have now a coffee break until 11:30.